And again, it's so we are very happy to have Mikoláš, Janota here. And again, we are trying to make here an environment which would attract people, with significant international experience. But I think in case of Mikoláš, it was an easy hire in a way because he brought a lot of his own money. So in this case, he is a recipient of the prestigious CIIRC CTU grant, which he brought here to this institute. And just a few words about Mikoláš. He received his PhD from the University College Dublin. Then he held a postdoc position at INESC ID Institute in Portugal, and also spent some time at Microsoft Research in Cambridge, in the UK. And his research interests are in logic, automated reasoning, and especially in the context of software development and verification. So again, we are very happy to have Mikoláš here and to hear more about his research. The floor is yours, Mikoláš.
So hello, everybody. So I know that I'm the last talk, and everybody's very tired after the whole day. So I'm skipping all the technical details, so it should be very easy to follow. So I really wanted to highlight what we do and why we do it. So because everyone is talking about ChatGPT, I thought I should also have ChatGPT in my talk. So I played with ChatGPT for roughly 5 minutes, and this is what happened. So I asked, well, there is this very famous proof that there is an infinite number of prime numbers by Euclid. Can you also show that there is always at least one prime number if I take 10 consecutive numbers? And I tried this recently with some undergraduate students, and everybody was shaking their heads. No, of course, there's going to be some prime numbers with a larger distance than just 10. But ChatGPT somehow, I don't know if they prime it to be very optimistic, but it just says, sure, let's modify the Euclid's proof so that we can show that there is at least one prime number in 10 adjacent numbers. And then it goes on and on about some proof that, of course, is not a proof. It's just some sequence of words because that's what it is, right? OK, so and now you say, well, OK, this is not so bad because if I ask someone on the street what's a prime number, they also don't know, right? So well, whatever, right? So this is not a disaster. But then I ask another question that is not seen here, but do you know what's the largest known distance between two adjacent prime numbers? And he said, there is a result that there are two adjacent prime numbers where the distance is like 70 million. And I'm saying, OK, so you're saying that for every 10 numbers, I can find at least one prime number in them, but at the same time, there are two prime numbers that are adjacent, and their distance is 70 million. I say, yeah, sure, exactly, that's what I'm saying. OK, so now you don't even need to know what's a prime number to see that this is not correct, right? So of course, the language models is great technology for translation, for summaries, for excerpts, but really it lacks the reasoning skills that we really would like to have in artificial intelligence. And my worry is that people will be forgetting that this is also artificial intelligence. OK, so Martin already mentioned something about logic, so I will also continue in the line of logic. So people have been going this for literally thousands of years. So Aristotle started with this, all men are mortal, Socrates is a man, therefore Socrates is mortal. And then after thousands of years, we came up with this nice notation that says exactly the same thing, right? So this is something that we call reasoning at some formal level. And so we would like to use this to discern truth from untruth, right? So this is this kind of simplified scenario where things are either true or are not true. And I really like this slide. It's a history of computer science in one slide, at least in my field. So first, Leibniz said, well, let's formalize everything and we will be able to calculate everything. And then this guy from Morava or wherever, he says, well, you know, there are some things that are neither true nor false. Okay? So this means that there will always be things that we will not be able to either prove nor disprove. Right? So this looked very depressing. Then it became more depressing because this guy said, well, there are things that we cannot compute. They are not calculable or undecidable. And then, you know, then all the computer science people from complexity theory said, well, there's a lot of things that are very hard, even though they are decidable, they're just very hard. So this is something we teach undergraduate students, and it looks very depressing. And then it's like, okay, what are you doing, right? Why don't you stop? So not all is lost. And the good news is that we can really solve interesting problems using logic. And this is essentially what I'm trying to show here in this couple of slides. So what do I mean solving problems using logic? So we start with some problem, abstract problem, but eventually would like that to be a real-world problem. We translate the question into a formula. We run some heavy engineered solver, which could be Vampire or the solvers I'm working on, and we get a solution, which gives us a solution back in the real-world problem, and we're happy because we have a problem to the we have the solution to the original problem. Sorry. So the solving here. Why is it beneficial? Because we have heavily engineered solvers that people worked on, spent a lot of time, and the solver will do a better job than if you solve the problem directly by yourself. Of course, not always the case, right? So you need the right tools for the right problems. So I work in an area which is called Satisfiability modulo theories, which stems from SAT solving. And again, I promise there will not be any technical details, but it's a very different beast than saturation-based provers, even though now these kind of provers that Martin mentioned and my area, they collaborate, they use each other. So it's something that focuses on specific fragments of logic that will be hopefully useful in practice. And one thing that is true nowadays, and maybe it will always be the case, but the challenge is that it requires sort of expert knowledge and effort to be able to use these solvers. And what we want is to get push-button technology. Okay, so what we want is, okay, now this is maybe not realistic, but you know, I still feel young, so I still think that we will be able to make some strides in that direction. So even though we're in this undecidable, highly complex background, we do want to get push-button technology. So just to get a little bit more concrete about the applications, so I mentioned software verification. Martin also mentioned that. So what do people do with software verification? So we have a program that's potentially incorrect. So what we ask the solver is there a bug? Right, so we write down a formula that represents the fact if there is a bug or not. Okay, so this is a question, it's a well-posed question, and so we can translate it into formal language, which is logic in our case, and we run it into a solver. Right? And there's a couple of things that can happen, mainly false. There's no bug, and we're happy because we have a bugless program and we can sell it to the customer. Then the other scenario that says true. Yes, there is a bug, which also is annoying, but is not as bad as shipping a bug to the customer, so we can fix it and repeat the process. However, there is a third scenario, which is the annoying one, is that the solver doesn't know. Right? So I send it to the solver, and the solver says, I don't know, this looks hard, I give up. Or just compute something forever and ever, and we don't know whether the program is correct, incorrect, has a bug. We just don't know anything. Right? So our research is in this zone where we're trying to avoid the scenarios where the solver doesn't know, but also want to be faster when it says true or false. Okay? Besides software verification, there's other types of domains that use SMT solvers. It is, in some sense, we're sometimes paying for being the back end of some of these technologies, because these guys can show some shiny results, but they need the solvers. I also wanted to mention some concrete examples from history that are essentially mainstream and industrial nowadays. So digital circuits, this is one of the first applications for SAT solvers where people were interested in checking whether there is a problem in one of the gates of the digital circuits. So you can send in some input and the circuit responds something. If it's wrong, if the gate is wrong, then I'll see a wrong output, but only for certain input, right? So the question is which input I should be sending in so that I do get a demonstration of a faulty component, and I know how many components there are and how they are constructed and so on, right? So this is something that we can ask the SAT solver. And again, this is roughly how we do it. So we construct one formula that represents the original circuit that should be correct and the faulty one. And we ask the SAT solver to tell us when do they differ. Okay? And then the SAT solver produces the input that we can send to the physical input, to the physical input of the physical circuit, and we can check if the physical circuit really is incorrect or not. We have to do it for all components, so there's a lot of technicalities which I promise to skip. Another thing is not necessarily software verification, but software testing. So this is a little bit similar to the circuits. So we were trying to come up with inputs to programs rather than just circuits. So this is some silly function that checks, it does an if statement, another statement, and if it reaches a certain point, it crashes. Right? And the question is, when does it crash? Well, I just run a solver that says, can you satisfy x divided by 3 greater than 5 and x less than 9 less than 3? If so, I know that the program will get to the wrong point. Right? So I run the solver produces a sample input, and then I run the actual program to see if it really crashes, right? Which might not if there's some issue with the modeling, but it's not a problem for testing. We want interesting test cases. Right? So this is a way how to get interesting test cases. I wanted to mention here there was this DARPA challenge in 2016 that was using these kind of technologies. So it was very nice. They had like autonomous computers that were somehow computing between each others for various challenges and hacking each other and so on. So this is something interesting to read about. There's also large projects, verification projects. So Microsoft, for instance, is trying to replace the whole HTTPS protocol with fully verified implementation. So these kind of things are interesting for the big companies these days because of cloud, right? So anything that has to do with the cloud communication is of interest to them. And of course, Martin also mentioned a lot of people are now doing smart contracts. So this is something that a lot of startups are doing these days. Well, okay. I don't have too much time, but just a few words about what I do. So we want to improve SMT solvers with machine learning, and we want to work on real-world problem, and we want to incorporate our expert knowledge about the solvers into what we do. So this is a very tiny, small example why and how we can use machine learning in solving problems in a specific domain. So I have this very trivial problem which says, for all x, x is y, such that x is less than y. And what we humans do, and what the solvers don't know how to do, is that we look at some examples and infer from them, right? So I for instance, check, I don't know, x is 3, and I see that 4 is greater than 3, and so on, right? So I can repeat this a couple of times and see, oh, actually, if y is x plus 1, then this is always true, right? So if I look at some small examples, as a human, I can generalize to a larger explanation that actually solves the problem in general. So this is something that completely lacks in the solvers these days. Another topic, a favorite topic of mine is quantifiers. So whenever we talk about all objects in some domain, we need quantifiers. So this, all philosophers are mortal. This is quantifier because we are saying all. This is very hard to work with, and so this is something that we were looking at. Like imagine that you have this formula where, I don't know, you have potential candidates, what to plug into the quantifier, and you're hoping to derive a contradiction, and you can use machine learning to order the candidates to arrive to the contradiction earlier. Okay. So this is again a little bit technical, but well, actually I could have talked more slowly, but it's fine. Okay, so some future outlook. So what is definitely lacking is this learning from experience. And I think Martin and I and Josef has been working on this, but we're still, I think, very far from really acquiring the same type of experience that humans gain. Like, for instance, when you learn fractions and you learn how to use math at the university. You'll gain a lot of abstraction that is completely lacking from the solvers. And the solvers, of course, they are much faster than us, but they don't have the abstraction. So this is something that is very interesting, and I think we're still scratching the surface with this. So we're hoping to incorporate machine learning, but it's more about the abstractions, I think, than the machine learning itself. A couple of challenges. We should never forget that this is very hard, theoretically impossible, but we don't care because we want to look at the real-world problems. But that means we need good examples. This is not easy, especially in the university environment. In Europe, we don't have that much contact with industry. I think we are trying to improve on that, of course. But even if you have contact, then how to work with them. This is very, very difficult. So we have this kind of a chicken and egg problem that hard to start the research in some directions if you don't have the data. So there's a bit of a disconnect between the people who write the solvers and who use them. And something that is maybe missing in these kind of NLP-style machine learnings or statistic-based is to come up with new concepts. So I would like to come up with new concepts like this x+1 example. Another problem in SMT is that there's a lot of these subfields. So there's string, integers, real, arrays, quantifiers. So there's like this zoo of problems that we're looking at. How to focus on the right ones. So these are kind of challenges in the field. And yeah, so thank you. I'm happy to take questions.
So thank you very much. We have time for a few questions. Any questions from the audience, please? Anyone? Yes, Patrick, please.
Thank you for the talk. Very interesting. I'm completely far from the field, so maybe it doesn't make sense. But when it comes to this software verification business, the fact that the software is running a big neural network, does it? I mean, at least when we do AI, proving that the software is doing the right thing doesn't mean that I mean, I have the feeling that it doesn't. It's just part of the story. Of course, you don't want to have bugs, but. So my question is, because some people have tried, I think, to import or export tools from software verification to neural network verification. So is there something sensible there, and things that can be integrated from your field?
Yeah, so this is a very active research now, how to verify properties of neural networks. Yeah, so I think one of the big motivation is, of course, this well-known attacks that you just change some small bits of a picture, and instead of a dog, it says, well, it's a house, right? But like for a human, it's not visible, the difference, but for the neural network, it's completely different because it's somehow sensitive to some noise. So this is something that you can formalize as a logic problem, where you say, if I change this input only a little bit, will it give always the same result? Right? So this is, again, like, so even though you're in a probabilistic setting or statistical setting, you can formalize this as a real, this truth-false problem, where you say, if I change it only a little bit, I pick some epsilon, am I guaranteed to be stable? Right? So these kind of attempts I have seen. I'm not active in this, so I mean, I'm sure maybe there's others here. But yeah, so this is. There's also other big attempts, like to use neural networks as controllers, right? So that you learn and then you reason about the network that the control just has some safety properties. And so it is possible, people do that. It looks scary because the network is huge. So it looks crazy, but yeah, people do it, yeah.
Okay, and my second question is for somebody who is doing very clean things, very theoretical, or about the properties of a software. I'd like to have your views about the way software development is going with a lot of AI assistance, like including using language model to debug or to test or to verify, of course, without any guarantees of any sort. So have you got any specific views on this trend in the software development industry?
So you're asking about the users of these.
So my question is for somebody who is caring about the proof, the verification, the properties. What are your thoughts about the evolution and the use of this tool and the way they are going to modify the software industry at large?
So GPT is now generating, some systems are generating code, right?
Yep.
So, and of course, you would like to know, is this correct, or does it, can one?
Yes, and also it can pretend to audit your code, saying that, or you can ask ChatGPT or Copilot X, is this code correct, and can you find the bug? So there is this appearance of code testing or code verification with these language model-based software, but I guess I'm trying to see whether there is things that people from your field either can tell or help these new tools to do better or to be used with more caution or whatever.
Yeah, so yeah, definitely. So definitely there is an opportunity for collaboration, and I think there have been some attempts, but so far I think also very little. Right, so one thing is that one issue for software verification is that you need to write down what it means for the software to be correct. Right? Because I just give you a piece of program, if it crashes all the time, maybe this is what they wanted, right? So, so someone needs to write down what it means to be correct, and this is a lot of work. You know how hard it is to write documentation, and people typically don't even bother writing documentation. Now you want specific logic formal specification of what the solver is supposed to be doing. And this is something that definitely could be generated by some NLP, right? So that you could generate a specification in a formal language and then try to verify it by exact symbolic methods, right? So these kind of things are possible. Of course, you're still getting in this who's gonna watch the warden, right? So you're still like in this. So someone ChatGPT generate a specification. Is it correct or not, right? Or I mean, also the other direction that maybe NLP suggests some issue with the software, and then you use some more exact methods to look for a bug. Yeah. So I mean, these are kind of these connections that we are interested in. So it's, it should not be a fight between the two methods, right? So we should. I'm just trying to highlight you need the exact methods as well for certain applications.
Okay, so thank you very much, Mikoláš, for a very nice talk. Thank you.